Okay, folks, the last video just cut me off with about 20 seconds left to go, and what I was just going to say, and it's kind of important as we segue into the next phase, our phase 3 out of the 3 phases we have, was that you can get order from disorder, but two major points. One, only if work is put into the system or energy is put into the system somehow. But two is the environment suffers. In other words, you can get a little bit of disorder, a little bit of order from disorder, but you get massive amount of disorder as a result. You get massive amount more entropy. And that salt water in the beaker example was a great example for this. You can have the sun energy coming in, okay, putting the work into the system to give you some salt crystals, order, you got some disorder, you got some ordered stuff out of that. Yes, you can do that with the energy in the system, but the second thing, the most important thing is you got massive amounts of overall disorder as a result. Okay, that salt water had to evaporate and become gas, which is super duper mega entropic. And so you got mega entropicism, I made that up, it's a great word, out of just a little bit of order. So there was a cost to that. When I learned this back when I was in high school, I was in my AP Chem class, and we talked about this, and I said, I'm going to use this at home. So the next time my mother wanted me to clean up the room, I said, Mom, you know I'd do it, but the problem is the universe is going to suffer. Of course, she looked at me like, what? And I said, well, if I put work into the system to organize my room, all of the energy and that I have to use to do that creates much more disorder in the universe, and so therefore I don't want to, contribute to the slow entropic death of the universe. I don't think it's a good thing I clean up my room. Yeah, that that didn't work very well. Okay, but try that one at home. Okay, not for professionals only. All right, let's dive into phase 3. Phase 3 is about Gibbs energy. We're not talking about like Barry Gibb from the Bee Gees. We all remember him. Bee Gees. Stay alive, stay alive, stay alive. Yeah, I should have been a singer. I'm in the wrong profession. No, not him. Right. Gibb. He was a scientist named after him, hence, Gibb. Gibbs energy, or it's called Gibbs free energy. Now, so far we've had delta H's, we've had delta S's, we've had enthalpy, and we calculated enthalpy changes, we calculated entropy changes, and now we're going to calculate delta G's, Gibbs energy changes. I know what you're saying. You're saying to yourself, why would I want to do that? Huh? Why would I want to do that? Huh? Because 1, it's awesome, and 2, it's chemistry, and 3, just because. Now, if something is a positive enthalpy, that means it's endothermic. That means it's usually not spontaneous. Remember that word spontaneous from the video ago, when we talked about spontaneity, whether or not an equation is set up to go in the direction it's set up to go, whether or not the reactants do want to make those products. If you've got it written right, is it written backwards? Okay. If it's a positive delta H, that usually, but not always, usually means non-spontaneous. If it's a negative or an exothermic reaction, that usually means it's spontaneous. In other words, an exothermic reaction is what nature prefers most of the time, not always, and allows us to create products and give off energy, and that's usually the way the reaction wants to go. When it comes to entropy, it's the opposite. When we increase our entropy, that means spontaneous, because things like to become disordered. They want to become, they want to have more microstates. And so that means positive is spontaneous when it comes to entropy, and negative is non-spontaneous usually. And then these are usuallys. And the problem with chemistry is there are, these rules, these guidelines, and then there are always exceptions. But with this bad Larry here, there ain't no exceptions. With this one, and actually you're going to see the equation for this very shortly. But when it comes to Gibbs free energy, it uses both enthalpy and entropy. And by using both those and considering both factors for a reaction, Okay, would it be exothermic? Would it be increased entropy? And looking at both of these together, we can come up with a definitive. Not just a usually, but a definitive as to whether or not an equation is written in the correct direction for it to be spontaneous. So if we can tell, we can get a value for delta G. You ready? Okay, here we go. Hold on to your butts. Okay. If it's negative, that's spontaneous. 100%, 100%, 100% of the time. The reaction is written the way it will go. It wants to do that. Okay, if a reaction gives you a positive delta G, then it is non-spontaneous. It is not written in the direction that it wants to go. It wants to go the opposite way. So there we have Gibbs free energy combines these two, and we get the energy, actually called free energy. In chemistry, what we're going to do is we're going to calculate how much free energy there is. And what that free energy means, it means the energy available to do work. Now, usually the physicist goes, oh, thank you very much, chemist. We'll take that free energy and now we'll do some nifty cool stuff with it. We'll make a heat engine out of it, or we'll do blah, 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 blah with it. So what we're concerned with is how much energy we get, and others are concerned with, well, what do you do with it? Okay, so how much energy do we get from a reaction? How much free energy, the energy available to do some work? Okay, well, let's stick with the chemistry for today, not the physics of what we would do with it. So this is a definitive. You get a negative for your delta G calculation, you're spontaneous. You get a positive, you are non-spontaneous. Okay, here we go, diving in. Now, delta G calculations are done the same way that delta H and delta S calculations are done. Chart, look up, boom, 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 boom. The one in the back of your book, Chang Chemistry, has your delta H's in the first column, middle column your delta S's, last column delta G's. Make sure you're looking at the right column. And delta G values are close, not the same, but they're close to delta H values. Delta H's and delta G's are measured in kilojoules per mole. How much energy is either given off or taken in terms of kilojoules per mole of material, moles of reactants. So these are similar, but they're not the same, because this will be a little bit different than this. So that's why we got to be careful when we're looking at the columns, because they do have similar values. But this one takes in consideration entropy, so it will have a different value than the enthalpy, although these will be close. And the entropy, remember, entropy numbers are small, but they do make a difference. And this considers both, so they are a little bit different than this. Okay, so they're both measured. So what are the similarities? They're both measured in kilojoules per mole. The delta G's and the delta H's both use zeros for elements at standard conditions in their basic form. So we go back to at least that being the same, because with entropies, remember, nothing can have a zero, because there's no absolute zero at which things would have to be zero at that temperature. You can't get that, so no entropy values are ever at zero. But delta H's can be zeros, elements. Delta G's also elements at standard conditions are zeros. So that helps us out a little bit in terms of making sometimes those equations a little bit easier to calculate. Let's do a calculation, all right? You're on the flip side here of your sheet. Now this one says, calculate the delta G for the following reaction at 25 degrees Celsius, meaning once again standard conditions. So you'd go to the back of the book, you'd look up the values under standard conditions, you'd find the delta G values, but you kids have had a rough week so far, so I've done it for you. You relax, you chill, you relax, have fun, you know, a little popcorn, drink a little root beer, okay? And watch the show that I'm putting on for you. Hope you appreciate it. I've already looked them up for you. So in this first one, 1A, let's write down what we have. So I'm looking at 1A. I mean, the first one on the back side of the thing is problem number 7. We did 6 of them the other day, so problem number 7. We have, so 7A, not 1A, but 1A in the back. 7A says we have some magnesium. That's not a good 2. Some magnesium, and we've got some oxygen, and we're going to make some magnesium oxide. All right, solid, gas, and magnesium is a solid. In Chem 1, I actually like doing this experiment where you take magnesium, you fire it up, have it get all nice and bright and burny, and make some magnesium oxide. Okay, so we want to calculate what the delta G is for this reaction. So what I'm going to do is the same, these are done the same way as delta H's and delta S's. The same thing. So I'm going to do, well, I guess I'll do both of them. Why not? But we take the sum of the products and subtract some of the reactants. Same thing. I hope you find these not that difficult. So let's take our sum of our products first. Here's a product. The delta G equals the sum of the product. So we have 2 magnesium oxides. I'll look up magnesium oxide. We have negative 569.6. So 2 times that. That's my only product, so that's it for products, minus the sum of the reactants. Hey, boom! These are both elements in their standard basic form, common form, oxygen, magnesium, room temperature, so what do they get? 0. So we're not subtracting bupkis. So in other words, we just got to multiply this by 2, and we have the answer to this problem. Multiply the answer by 2, and hopefully you'll get 1,139. 1,138 plus 639. Yeah, that's going to come out to be, double that. You'll get 1,139.2 kilojoules per mole for our answer for that one. All right, let's quickly do the second one. That one was TE. Just TE, man. Too easy. Too easy. Okay, so let's try B. All right, B, what do we got? We've got some B. Here we go. That's ethane. Ethane, we're going to combust it. Now we know that combustion reactions produce a lot of heat. They do. Oh. The other thing about the last problem, A, you got a negative value. That negative value, what does that mean? What does the negative delta G mean? It means 100% you can guarantee that that's the way that reaction wants to go. Magnesium wants to combine with oxygen and form magnesium oxide. And that's what metals want to do anyways. They want to oxidize, and that's called oxidation. So that's what it wants to do. That's the way it's going to go. Yeah, give it a chance, it'll do it. All right, so this is ethane. Ethane wants to burn in the presence of oxygen. You give it a little bit of a spark, and it sure does that. We all remember reaction, carbon dioxide and water, okay? That's what we get with combustion reactions. Classic combustion reactions, CO2 and H2O, making sure we balance it. We got a 4 here, what else? We got 6 here. Okay, so balanced, ready to go. We just gotta make sure we do all the math right, because there's a lot of things in this one. Every one of those has a coefficient. Okay, so here we go, delta G equals the sum of the products for CO2s. CO2's delta G is negative 394.4. Then we have to add, that's the sum of the product, 6 waters. H2O liquid, negative 237.2. Okay, those, so I'm going to bracket this out. That's the sum of my 2 products. Subtract the sum of the reactants. The first thing I have is 2 ethanes. Ethane, negative 32.89. Negative 32.89. Add 0. That's a big fat 0 because it's elemental. Oxygen gets a 0 for its delta G, just like a delta H. Okay, we're going to do the math on this. You have to be careful. Make sure you multiply that. You get a big negative number. Add another big negative number. You get a really big negative number. Then you subtract the negative, which means adding this to it. So just be careful of that. Make sure you double it. If you do the math on that, I have faith in you. You'll come out with negative about just under negative 3,000. So this comes out to be just under negative 3,000 kilojoules per mole, which means that's a lot of energy given off. This is spontaneous. This is the way it wants to go. Hydrocarbons do want to burn in the presence of oxygen. They'll certainly do it if you give them a reason. Give me a reason. Come on, bring it. Keanu Reeves, thank you. Good impression. I know. And there you have it. This would be a spontaneous reaction, giving off lots of free energy to do some work. All right, and that's how we do delta G's, just like delta H's and delta S's, and the difference between delta G values is they encompass both H and S, so we can get a definitive spontaneity or not spontaneity. All right, video 1, done, boom.